What is up, everyone, and welcome back to my channel. In my 8 years since I worked in this domain of creating measurement programs, not one time have passed and I've not wondered if my programs are stable and correct. And to make sure that what I was doing was not to waste my time and my colleagues as well, I started looking for answers on how to check and how to improve my work. This is why my latest two videos were about how to check your elements that construct your alignment, and this is why in this one we are going to talk about alignment iteration and why is it important. So, let's get right to it. We must first remember 3 to 1 alignments or RPS alignments, because they are the perfect fit for the reason we have to use iterative alignments. And our objective is to make our alignment stable enough to rely on the measurement results. And the tool after we make the 3 to 1 alignment is to set the iteration and to restrict it with a delta value. With this iteration, we have a 98% chances to have reliable measurements. And 3 to 1 alignments are used mostly on parts with unregulated geometry form, so it's necessary to specify all 3 coordinates of all 6 points. So I'm guessing I don't need to tell you why 6 points in 3 to 1 alignment. In order to explain iterative alignments, I put together this part and its technical drawing right here that we can see right here, from where we are going to talk about only the alignment. So these datum targets right here. So we can notice from the drawing that by measuring the first 3 points A1, A2 and A3, we will determine the first 2 rotation on ZX plane and YZ plane, and the translation on the Z axis. Then the next 2 points B1 and B2 will determine the rotation around the Z axis or the XY plane, use it as you prefer, and the translation on the X axis. Then with the last point C1, we will determine the origin on the Y axis. And in these specific cases, a precise alignment is nearly impossible without an iterative alignment. So where does iterative come from? Well, it means that the alignment has to be done in multiple steps, and each step will be calculated relying on the previous steps. And when the iteration is complete, all the points used in the alignment will be as close to the nominal data from the drawing as it can be according to the deformations from the part. So in our case, the first iteration can look like this. Notice that the points are far away from the target value, but the software will calculate the rotations and the translations, and with the deviations from the calculation, it will make a sum, and that will be our delta value. From that, it will go and make again the alignment until it reaches the desired delta value. So in our case, let's say that we want a delta value of 0.01 at the end of the iterations. Keep in mind that you can use the golden rule for the iteration of the alignment. 10% of the smallest tolerance that you have on the drawing should be enough to set on your delta value. So let's say that my smallest tolerance on the drawing now is 0.1, that is why I choose 0.01 for the delta value. So notice that our first iteration has a delta value of 0.7, and just as I said, the points are far away from the target value. Then at the second iteration, our points will be closer to the target value, and the delta value will go down to 0.1 to 0.05. And if you are wondering, that much? Yes, that much. The software is capable to adjust fast to the form of the part. And in the last iteration, notice that the points are right where they are supposed to be, and we will be within the values of 0.01 or below that for the delta value. This means that the software has calculated the position of the part in the volume of the measurement from the machine. It has calculated the inclinations of the part and everything it needs to in order to measure correct the elements that you choose from the part. Now let's simulate this on Calypso and see what happens.
Okay, so we are here in Calypso and we've extracted the points that we need to do the alignment, and we have done the alignment in RPS method. Okay, so it's the RPS method. Notice the points right here. You can also check the nominals so they can be according to the drawing that you are working on. I can see here some deviations and I will correct them. So these are the coordinates from the drawing. So okay, A1 is good, A2 is good, A3 is good. Let's check B1, and here it should be like this. Here it should be like this, and here it should be like this. Okay, the axis looks good, and we want to check the loop, and I've inserted the loop. This is the formula for the loop if you want to use it on your base alignment, and this is the delta value that I want to have at the end. Okay, looks good. No, and let's simulate the measurement. And we do have the report right here. Let's check the report after the measurement. Okay, so we do see that the first time it was made, the alignment, we have some differences on the measured values. So these are the differences on A1, for example. On z-axis we have a deviation on the point of 0.0 minus 0.05, so this is not good. On A2 0.08, but we want to check the delta value for A1. So for A1 the delta value was 0.17. This is not good because we want the delta value to be around 0.01 or below that. So the software calculates the delta value and it goes and makes the alignment again, and we can see here in the branches that this is number 2, the iteration number 2. Okay, so the delta value for number 2 was 0.015. so this is good, but it's still not below 0.01, so it goes and makes again the alignment. Okay, and this time the delta value is 0.009, so it's below 0.01. so yeah, now the alignment and everything should be fine. Okay, so keep in mind that if you do only one iteration, you will have this deviation on the delta, so on the sum of all the axes, the rotations, the translations of the axis and everything. And this is why you need to do the iterations on the alignment. Okay guys, this is it for today. Thank you for watching. I hope I helped you with this information, and until next time, keep learning and keep improving until you become better and better. This is the way I work. This is the way I want to work. This is what I stand for. So have a nice one. See you next time.